Hello everyone, welcome back to the video lecture regarding the self-controlled synchronous motor drive employing a load commutated thyristor inverter. So we already discussed true synchronous mode and self-controlled mode of operation of a synchronous motor drive. In a true synchronous mode, as you all know, it is an open loop mode. An independent oscillator is used for varying the frequency of the inverter. There will not be any feedback path, but in a self-controlled mode, it is a feedback control mechanism. We are using the voltage sensors, and from that we are deriving the speed measurement, etc. So we already discussed some of the schematics of true synchronous mode and self-controlled mode of operation. It is we discussed this self-controlled mode. Here you can see that we are using either rotor position sensor or voltage sensor, and from this information we are finding out the actual speed, and it is compared with the set speed. Similar way, in a true synchronous mode we are using a separate oscillator which is actually providing or varying the frequency. And let's discuss one of the major mainly using synchronous motor drive. The name is self-controlled synchronous motor drive employing a load commutated thyristor inverter. As the name implies, it is self-controlled. It can be acting as operate in the open loop mode also. So this is the circuit diagram for the particular drive. Here we can see that it is a three-phase AC waveform. We have a rectifier, controlled three-phase controlled rectifier. Here a three-phase inverter, and you can see that input to the inverter there is a large value of inductance. This inverter is now it is a current source inverter. So current is constant by using this value of this inductance LT. So this is current source inverter. So load state converter is actually current source inverter, and source state converter is the rectifier, fully controlled rectifier. And as you all know that this controlled rectifier can be acting as a line commutated inverter. A rectifier can be acting as a line commutated inverter. Only the condition is that you know that it is acting as rectifier for the value of firing angle between 0 to 90 degree. This is acting as inverter for a firing angle 90 to 180 degree. And similar way, this converter is also acting as rectifier for a firing angle of 0 to 90 degree, and for 90 to 180 degree it is acting as a inverter. And here commutation is actually happen by not using any line voltages. Line voltages are connected to this converter. Here the commutation is by using the induced voltages, here stator induced voltages. So that the synchronous motor is the load. So actually load commutation is happen in case of a load side converter. So that is it is known as load commutated converter. And here for this rectifier, source state converter, it is acting as rectifier for a firing angle 0 to 90 degree. Suppose this is acting as inverter for a firing angle 90 to 180 degree. Then you can see that power is flowing from this side to this side. Okay, power is flowing from this side to this side. AC is converted into DC. Then it is given to the current source inverter, and it then input to the current source inverter, and this DC is converted to again to AC, and it is given to the stator of the synchronous motor. For firing angle of the source side converter 0 to 90, and firing angle of load side converter is 90 to 180 degree. So that is the motoring operation. Suppose if you want to generation or braking operation, you should change the power flow from load to the source. For this case, for that particular case, for braking operation, this converter should be acting as rectifier. This should be act as inverter. For that case, the firing angle of this particular load side converter is 0 to 90 and this converter is 90 to 180. Now the power is flowing from this side to this side. So both the motoring and generating actions are taking place depending upon the firing angle of these two converters, source side converter and load side converter. And let's see the sum of the points I have written here. A CSI fed synchronous motor drive may employ load commutated thyristor inverter. When a synchronous motor is fed from a CSI, it can be operated in a self-controlled mode or it can be operated in a true synchronous mode. When fed from current source inverter, synchronous motor is operated at leading power factor so that the inverter will work as a load commutated inverter. A load commutated inverter fed synchronous motor under self-controlled mode is actually given here. The source side converter is a 6 pulse line commutated thyristor converter. For a firing angle 0 to 90 degree, it works as line commutated fully controlled rectifier delivering the positive VD and ID. For a firing angle 90 to 180 degree, it works as line commutated inverter giving minus negative VD and positive ID. So when a synchronous motor is operating at leading power factor, thyristor of load side converter can be commutated by stator induced voltage. That is in the same way as that of a line commutated converter are commutated by line voltages. So it is this voltage is from load side, so it is load commutation. Commutation of thyristor by induced voltage of load is known as load commutation. So load side converter will act as inverter for 90 to 180 degree. This alpha L is representing the load side commutator firing angle. This alpha S here written is the source side commutator, source side converter firing angle. And for 0 to 90 degree, this is working as rectifier. So if it is rectifier, this source side converter is rectifier, load side converter is inverter, power is flowing this side. If it is rectifier, it is inverter, power is flowing from this side. So you can motoring operation and generating operation, both braking operation can be achieved depending upon the firing angle. And that is the motoring operation. You can see for 0 to 90 degree alpha S, source side firing angle is 0 to 90 degree and load side converter firing angle is 90 to 180 degree. Then it is motoring operation. Source side converter acts as rectifier and load side converter is act as inverter, causing power flow from AC source to the motor. Similarly, generating operation, this alpha S is now it is 90 to 180 degree and alpha L is 0 to 90 degree. Then load side converter works as rectifier and source side converter is acting as inverter. Power is now flowing from motor to AC source. That is a generating operation or braking operation. And you see the inductance LD, that is reduces the ripples in the DC link current, that makes the current as constant. That is actually making that particular converter as a current source inverter. Due to LD, load side converter works as current source inverter. And for operating in the self-controlled mode, we need to ensure rotating magnetic field speed should be same as rotor speed. This condition is achieved by making the frequency of load side converter output voltage equal to the frequency of induced voltages in the armature. Normally we are using, in order to achieve the self-controlled mode of operation of this particular drive, we are using Hall's effect sensors for sensing the voltages used to obtain the rotor position of the rotor position information. In order to obtain the rotor position information or as a rotor position sensor, we are using Hall effect sensors. The difference between current source inverter fed induction motor drive and synchronous motor drive is that induction motor drive uses the forced commutation and synchronous motor drive now it is using the load commutation. So this is the circuit diagram. Never forget this circuit diagram. This is important as far as the synchronous motor drive is concerned. And understand this working, motoring and generating operation. And this is the one of the point you should remember. there will be a possibility of commutation failure in the circuit. We are using two converters, that is rectifier and a inverter. In that we are normally define a commutation lead angle. That is, we cannot control the firing angle up to 180 degree, 90 to 180 degree, but it usually 90 to 165 degree, like that. So there is a commutation lead angle we define for every converter. So when working as inverter, firing angle has to be less than 180 degree to take care of commutation overlap and turn off of thyristor. Commutation means the process of turning off of thyristor. So commutation overlap means that when one of the thyristor, when we are turning off, it does not go to the off stage abruptly or very within no time it won't turned off. It will take a particular time to turn off. In the same time, the other switch in the same leg we turned on. So in that case, there will be a chance of turning on of two devices in the same leg. That will cause a direct short circuit. So we should avoid commutation failure. Commutation overlap, we should that also will make reduction in the average output voltage. So we should taken care of commutation overlap in the during the firing pulse generation. So normally commutation lead angle is defined as beta L is 180 minus alpha L. Beta L is the load side. This is defined for the load side converter. This is the commutation lead angle beta L, that is 180 minus alpha L. Alpha L is load side converter firing angle. So actually you understand one point. When you are defining the lead angle, this angle actually the angle by which voltage and current are displaced. That is this actually define the power factor. The power factor angle means that is the phase displacement angle between voltage and current phi. So now here if we are defining a commutation lead angle, now the power factor become cos beta L. The motor operates at leading power factor with a power factor angle beta L. So what happened when the lower value of the beta L means the higher motor power factor and lower inverter rating is required. So our aim is to make this value is lower. Okay, this value is lower. If you are increasing this value, this will become lower. Hence the power factor can be increased. So in a simple control scheme, drive is operated at fixed value of lead angle. Normally we are fixing it as a constant for the load side converter working as inverter, and as beta L is equal to 180 degree or alpha L is equal to 0 for working as rectifier. So if a load side converter is working as inverter, then we are making this beta L as constant, which is equal to beta L as a constant. Then when it is working as rectifier, beta L is equal to 180 degree. Okay. When it is working as inverter, it is a constant value. Beta L is a constant value, beta LC. And when it is working as rectifier, it is equal to 180 degree. Beta L equal to 180 degree or alpha L is 0. So based on that, there is a closed loop speed control of synchronous motor drive employing load commutated thyristor inverter schematic diagram. This diagram you can see that here this part is well known. This is speed control loop, outer speed control loop, inner current control loop. Okay, this speed is actually sensed from terminal voltage sensor. The inside here it is actually the frequency control that information also obtaining from terminal voltage sensor. So this is a closed loop schematics. We will discuss this in the next lecture.